In 1874, 28-year-old mathematician Georg Cantor published what seemed like a modest technical paper about sets of numbers. But it was a Trojan horse. Hidden inside was an idea that would reshape mathematics. Infinity comes in different sizes.
Cantor's ideas were earth-shattering. People didn't have the expectation that there would be different sizes of infinity, and so it opened up this whole new realm.
We now celebrate Cantor as a genius who just changed the shape of mathematics.
That is, a kind of myth.
Newly uncovered letters between Cantor and a colleague point to a more complicated reality. An origin story built on a secret and a theft.
I couldn't believe my eyes. Those were the letters that I was looking for.
So how did a single paper become one of the most important proofs in math? And who was left out to get it published? For thousands of years, mathematicians treated infinity like a hall of mirrors. Endless, but untouchable.
Infinity as a concept was a taboo.
It was a philosophical question.
The only kind of infinity mathematicians would accept had a name: potential infinity. A sequence of numbers could go on forever, but forever was a process, not a destination.
The numbers are infinite, yes, but they're only potentially infinite. You can have more and more numbers, as many as you want, but you will never have all of them as a completed totality.
By 1872, two German mathematicians, Richard Dedekind and Georg Cantor, were beginning to push back against more than 2,000 years of mathematical caution. They were independently wrestling with the same idea: constructing the number line. At the time, mathematicians assumed the number line was incomplete because it was full of gaps. Take the stretch between two natural numbers. Zoom in and you find infinitely many fractions. But no matter how far you zoom, certain numbers never appear. There are real numbers, like the square root of 2, that no fraction is equivalent to. You can get closer and closer without ever precisely landing on it. Dedekind wondered, what if you could define a real number by the gap it fills? What if the gap is the number? Using a method now called a Dedekind cut, he showed how to construct a number line that contains every possible limit. Independently, Cantor also built a complete and continuous number line.
You have these two guys who are formalizing the mathematical concept of the real number line. They were on the same wavelength.
Dedekind and Cantor's work revealed something unsettling. Infinity wasn't hiding at the far end of the number line. It was there in every interval. For the first time, infinity was a real destination.
So they exchange papers, and then by chance they meet.
In the summer of 1872, Cantor and Dedekind met while vacationing in a Swiss village.
Cantor and Dedekind, they would make very different impressions if we could see them on the screen.
Cantor, he was very emotional. He wants to show that he can be a renowned mathematician.
While Dedekind is quite the opposite. He was a quiet man, modest and calm.
Dedekind was much older than Cantor. He wasn't a guy who was crazy to get recognition.
Despite their differences, Cantor and Dedekind were united by what they dared to do: follow the path that led to infinity. In November 1873, Cantor wrote to Dedekind, kicking off a lively mathematical correspondence.
These letters are quite famous. They belong to the most well-known correspondences in mathematics in the 19th century.
This correspondence is key to understanding the origins of infinity. Cantor's letters survived, but Dedekind's side of the exchange was known only from notes he later wrote. The originals were thought to be lost.
We see these questions coming from Cantor and a real exchange of new ideas in mathematics.
Allow me to put a question to you, Cantor wrote to Dedekind. It has a certain theoretical interest for me, but I cannot answer it myself. Perhaps you can. Cantor's question was about the collections of mathematical objects called sets. A set can be finite, like the numbers 1 through 10, or it can be infinite, like the natural numbers, which can go on forever. To compare the sizes of two sets, mathematicians try to pair them up like ballroom dancers, where every element of one set corresponds with a unique element of the other. To see this in action, let's compare the even numbers to the natural numbers. At first glance, there seem to be half as many evens. But pair them up, and every even number finds an exact match with a natural number. Counterintuitive as it seems, the two sets are the same size. Both are what mathematicians call countable.
So Cantor presents the problem, what happens with the real numbers?
The real numbers include all fractions, as well as numbers like the square root of 2. In his letter to Dedekind, Cantor asked a simple but radical question. Are the real numbers countable? In other words, can they be placed in one-to-one correspondence with the natural numbers? According to Dedekind's notes, he wrote back that he didn't know how to prove that, but that he had proved something else. The algebraic numbers, or the numbers that you get as solutions to algebra problems, could be put in one-to-one correspondence with the natural numbers.
In other words, the algebraic numbers are countable.
To find out if the real numbers were countable, Dedekind suggested that Cantor focus on just a small part of the number line, between 0 and 1.
What Dedekind told him is that you don't really need to consider all the real number line, only just a little interval. And if that is countable, if you can create a list for that, then it's more than enough.
If the real numbers were countable, then you could create a complete list of them and match each one with a natural number, with none left over. But Cantor showed this was impossible.
Cantor proved that for any countable list of real numbers, we can produce a real number that's not on the list.
Cantor sent his proof to Dedekind, who, according to his notes, improved on it significantly. Today, here's how we think about the argument. Assume that we already have a complete list of real numbers between 0 and 1. They can be matched perfectly with the natural numbers. Then look at the first digit of the first real number, the second digit of the second, the third digit of the third, and so on. Now let's change each of those digits and combine them to create a new number. This new number cannot be anywhere on the list. It differs from the first number in the first decimal place, and so on. That means that the real numbers cannot be put in a one-to-one correspondence with the natural numbers. They're uncountable. The implication was extraordinary. If the real numbers can't be counted, but the natural numbers can be, then one infinity is larger than the other.
So there's at least these two infinities, and that's quite profound. The heavens have opened, and we realize that there's this vast new realm to look into and investigate.
If infinity could be measured, then it had to be treated as a legitimate mathematical object. Cantor knew that not everyone would be willing to accept that.
He knew it was revolutionary. He knew this can have really deep implications to mathematics.
It was simply not the way ideas were presented in mathematics before.
There was a big obstacle in the way of publishing these ideas. Leopold Kronecker, a mathematical gatekeeper who was on the editorial board of one of the most prestigious journals in the field.
Kronecker is wholly on the side of the finite. He wants to purify pure mathematics, restricting everything to what you can construct on the basis of the natural numbers.
Just imagine you have a very important message you want to share with people, and you know you cannot tell anybody because it will just lead to hostility.
Cantor would have to find a way through the gates of the establishment. He began to build a mathematical Trojan horse, a paper framed around the countability of the algebraic numbers. First, he presented Dedekind's proof, nearly word for word. It was the perfect decoy. Just below it, Cantor smuggled in his own argument, refined with Dedekind's help, showing that the real numbers cannot be counted. Together, the two results pointed to the radical conclusion: infinity comes in different sizes.
It is a very short paper. It's barely 4 pages long.
It's famous because it proves something about the set of real numbers, but the title of the paper doesn't highlight that. It reads on a property of algebraic numbers.
I have no doubt Cantor would have preferred to write an article with the title, "There are different sizes of infinity. Look at this crazy shit," but he couldn't.
Cantor's paper was published in Kronecker's journal, under Cantor's name alone. Over the next few decades, the idea from Cantor's paper took root in the mathematical establishment, forming the basis of set theory, a framework that would become the unifying language for all of mathematics.
There's this famous quote, "No one shall cast us from the paradise that Cantor has created for us."
Today, much of modern mathematics is written in the language of set theory.
In set theory, you can contemplate essentially any kind of mathematical structure whatsoever. The picture that emerges is this incredibly tall tower of mathematical reality in which more and more sets appear. What set theorists are doing is trying to understand the nature of this hierarchy.
Today, Cantor is celebrated as the architect of set theory and as a central figure in the foundations of modern mathematics.
The story that we usually tell about set theory is that we owe everything to Cantor alone.
It's easier to tell an interesting story with just one single character who is the heroic figure.
Some suspected that Cantor's ideas hadn't emerged in isolation, but the historical record was incomplete.
The letters that Dedekind sent to Cantor, which would include the proof, were lost.
We thought they were lost forever.
To prove how much Dedekind had shaped Cantor's famous paper, the missing letters would have to be found. In 2024, mathematician and journalist Demian Goose began searching for Dedekind's letters to Cantor.
You find 100 sources and you want to check everything.
The search led him to an archive at the University of Halle in Germany, where Cantor had held an academic position.
So I went there and they handed over just like a little binder with all the letters. That was just like unbelievable.
There was one dated November 30th, 1873. Goose knew immediately what it was.
I was just so excited because I knew this must have the proof that I was looking for.
It was Dedekind's proof that would later appear in Cantor's famous paper without attribution. The set of all algebraic numbers, Dedekind wrote, can be put into a one-to-one correspondence with the domain of all natural numbers.
It was just like a shock.
With Dedekind's letter in hand, Cantor's reply, sent just before the paper was published, suddenly made more sense. "Your remarks," Cantor wrote, "which I value so highly, were of great assistance to me."
Cantor published the paper, stole his friend's result, and put that result on the title of his paper, right? Nasty business.
I don't see any way of really letting him go without some kind of accusation of plagiarism.
The newfound letters offer a glimpse into mathematics as a process shaped by people, their ambitions, their collaborations, and their choices.
Math is a collective enterprise. One has to be careful with the ethical sides, just like it happens more generally with any scientist.
Goose hopes the letters will reshape how mathematicians tell the story of one of the field's greatest discoveries.
A lot of people are still very emotionally invested in this story about Cantor and set theory. There is a reason, a valid reason why we acknowledge Cantor. But I think it's also more interesting to then tell the complete story.